Okay, in this next video, we're going to continue to look at the relationship between electricity and magnetism. Specifically, what is the magnetic field pattern of the magnetic field due to the current in straight wires and solenoids, so two different circumstances, and how we can increase or decrease the strength of this magnetic field. All right, but we're going to cover it in parts lah. So in this video, it's not going to be the whole thing. So the key idea one, which is super important that you need to understand, is that a moving charge or current produces a magnetic field around it. Okay, a moving charge or current produces a magnetic field around it. What is this moving charge thing? Basically, I'm trying to bring things, connect back with the very earlier topics you learned. When we started this whole electricity and magnetism theme, right, started with a static charge, right, a single charge, whether it was a positive charge or a negative charge that we call an electron, right, and when a charge moves, we get a current. Okay, so if you remember in a circuit, right, you have your positive and your negative, and when you have a charge that moves, so let's say you have a positive charge that moves, you get a current. A flow of charge is a current. So a moving charge or a current produces a magnetic field around it. So if let's say you have a current, so if you have a current flowing through a wire, right, basically a current is made out of moving charges, but a current flowing through a wire, just like what Ørsted discovered, you will get a magnetic field produced around it. Some important things about this magnetic field: the magnetic field consists of concentric circles. Concentric means they have the same center. All the circles have the same center, which is the straight wire where the current is flowing through. And the magnetic field is stronger closer to the wire. So if you can see, the magnetic field here is closer. The magnetic field lines are closer here than they are here. Here is further apart. And remember, the closeness of the field lines tell you how strong the field is. So magnetic field closer to the wire is stronger, and hence they are drawn closer together. And magnetic field lines further away from the wire are drawn further apart because they are weaker. Okay, they are weaker. The direction of the magnetic field can be determined by the right-hand grip rule. How? Like this. Okay, so if you have your current flowing up, you use your right hand. That's why it's called the right hand grip rule. I hope y'all can tell right from left. You use your right hand and you grip it. Your thumb points in the direction of the current, just like this. Your thumb points in the direction of the current. The current is flowing upwards, so your thumb points upwards. And then your fingers will curl around the wire in the direction of the field. So because your fingers are curling around this way, the field also curls around this way, and so the field is anti-clockwise around the current, like so. Okay, so the right hand grip rule gives you the direction, whether it's clockwise or anti-clockwise, around the current carrying conductor, and it's always concentric circles, stronger closer together, weaker further apart. Okay, so yes, thumb points in the direction of the current, fingers curl in the direction of the magnetic field. So what happens when we reverse the direction of the current? Let's say the current now flows downwards. What will be the direction of the magnetic field? Okay, so your thumb, instead of pointing up, points down, and you notice that now your fingers curl around in the opposite direction, right? So when you reverse the direction of the current, the magnetic field's direction is also reversed. Okay, and if the current now was going downwards, your thumb points downwards, this will curl around it like this, and it will go clockwise. Okay, so you reverse the direction of the current, you just reverse the direction of the magnetic field. Okay, important thing to know lah. But of course, as long as you understand, it's fine. Okay, so the pictorial representation of magnetic field patterns around a straight wire. These are some ways that we talk about it, because we don't always want to draw 3D, right? It's not easy to always draw 3D. So sometimes we look at 2D. Look at 2D means we're looking either from the wire, we're looking straight down from the top, or we're looking straight down from the bottom. Okay, so imagine you're looking down at a wire. So this is your wire. Instead of like this, you're looking down at it like this. Okay, and then the field will be around it like that. Make sense? Okay, so when we do that, how do we represent which direction the current is flowing? Okay, a circle, this represents the wire, Okay, this is a wire with a dot in the middle. The dot represents current flowing out of the plane of the paper towards you. Okay, so can you imagine this is a wire that is that you're looking through like that. Okay, you're looking through like that, and if it's a dot, it means that the current is flowing out of the paper towards you. Okay, the current is flowing out of the paper towards you. And so if you to use your right hand grip rule, what will you do? Your right hand grip rule, your thumb will point towards you out of the paper, and it curls around this way. So you will get a anti-clockwise magnetic field around it. Concentric circles, closer here, further apart there. Can? We usually use solid lines for magnetic field, not dotted lines. Okay, so the magnetic field can be in solid lines. Okay, solid lines. Okay. Okay, anyway, what about the opposite direction? Okay, so note how the distance of field lines get further and further apart. Okay, what about the other direction, right? The other direction, this is a wire with an X. If X, it means it's going into the paper. Okay, so X represents currents flowing into the paper. Okay, into the plane of the paper away from you. So if you use your right hand grip rule, your thumb will now be pointing into the paper. I hope this makes sense, into the paper. And so this will curl clockwise direction, and your magnetic field will be in a clockwise direction. Okay, how do I remember this thing? So I personally, how I remember it when I was a student is that, you know, when you go treasure hunting, right, X marks the spot, right? So if X marks the spot, what do you do when you see the X? You dig, right? You dig into the paper, like you dig into the floor to find it, right? So that's how I remember it. When I see X, that means I need to dig in, so X is flowing into the paper, it's underground, right? I've told this to some people before. Some people laughed at me and said it's very confusing. The way that they usually tell students, which to me I find is not any less confusing, is you look at an arrow. Okay, you look at an arrow, like a bow and arrow. You know a bow and arrow? So you know an arrow like that, right? So usually has like these feathers things, right? Okay, so the feather, right, usually is like the arrow. Okay, so the arrow tip is a sharp point, and behind usually the arrow is got four feathers, right? So if you look at the arrow, let's say the arrow is flying towards you, like the arrow is flying towards you like this. If it's flying towards you, what do you see? You see the tip of the arrow, which is just a dot, right? So if you see this here, a dot, if you see a dot, it's the tip of the arrow flying towards you. But then if the arrow is flying away from you, what do you see? You see the tail of the arrow, and the tail of the arrow is the feathers, right? And the feathers will form a X shape, right? Because the feathers will be like this, right? Because got 4 feathers, right? Yeah, I never really draw properly. Yeah, so the feathers is like that. So when you see a X, it is the arrow flying away from you. So the arrow is flying away from you into the paper. I don't know which one is clearer to you, which one floats your boat. I don't know if you've heard better ways to remember, but these are the 2 ways that you can try to remember. One is X marks the spot. You see the spot, you dig in, so it's into the paper. I use that. The arrow method is the other way that people use. So the tip of the arrow or the tail of the arrow. Okay, so use whatever helps you to remember. But one important thing to know here is that the direction of the magnetic field of a current carrying wire reverses when the direction of the current is reversed. Okay, this is what I said just now, and it's important, and it's an important idea to remember. Okay. Alrighty. Okay, so how does the strength of the magnetic field around a straight wire vary? Okay, when the current varies. So let's say this wire, everything is exactly the same except the current in this wire is less than the current in this wire. Okay, so the current in this is weaker than the current here. What do you expect the magnetic field? I think it's quite intuitive. You expect the magnetic field of I1 to be weaker than the magnetic field in I2. And how do you show that? You show that by how many field lines there are. Again, usually magnetic field lines we draw solid lines. Okay, so you can see that this is weaker than here, because the strength of the magnetic field of a current carrying wire increases when the current is increased. Okay. Alright, so now we're going to hop over to handout 2, question 1. I'll see you in the next video.